Hello and welcome to our live webinar on the Energy Information Nexus, an NSF Industry University Cooperative Research Center. My name is Todd Cleland. I'm Senior Director for Corporate Relations at the University of Washington, and I'll be the moderator for today's webinar. Today's webinar will cover a planned NSF Industry University Center focused on new energy architectures for powering data centers. These are technologies that would make data centers both greener and more sustainable. Before we get started, just wanted to briefly display the standard UIDP disclaimer covering events, publications, webinars, videos, and so forth. Now I will briefly introduce today's panelists. Again, I'm Todd Cleland from the University of Washington. Today you'll be hearing from 7 faculty experts. From the University of Washington, we will have presenting Stuart Adler and Dan Schwartz. From the Colorado School of Mines, you'll be hearing from Greg Jackson, Amy Landis, and Robert Braun. And from the University of California, Irvine, we have Jack Brower and Irina Zanyuk. And with that, I will turn it over to Stuart Adler from the University of Washington. Stu?
Okay, thanks, Todd. Hi, everyone. Thank you for taking your time out from your busy schedules. Before proceeding, I'd like to acknowledge my colleagues Jack Brower from UC Irvine and Greg Jackson from the Colorado School of Mines. Together, we have proposed the creation of a new NSF Industry University Cooperative Research Center entitled the Energy Information Nexus. The goal of the EIN is to help companies in the cloud energy supply chain develop new ways to power the cloud, which reduce emissions and eliminate bottlenecks to growth. In the process of forming the center, we've spoken to a number of people in the cloud service sector, as well as people who provide energy infrastructure for data centers. What came through pretty clearly is a concern about meeting the growing demand for cloud services, while also meeting goals and challenges associated with electrical power. These concerns touch on a number of issues, but chief among them is the availability of electric power in areas desirable for new data centers, cost and reliability of electrical infrastructure in general, including all the backup systems needed to ensure uninterrupted power, and the carbon footprint and other emissions associated with electrical power. Based on these concerns, many of you in this audience have begun to explore, or at least think about, new technologies and approaches that have the potential to free data centers from the constraints of electrical power. Our proposed center focuses on power production and storage technologies that can be embedded right into the data center itself, allowing a much greater control over the availability and emissions, as well as other possible synergies. One possibility is incorporating rechargeable batteries at the rack or pod level, allowing off-grid operation for hours or days. Besides eliminating the need for centralized backup, this would allow data centers to selectively purchase and store low-cost excess wind and solar power. This is a huge and growing opportunity. For example, just in California in the spring, an average of 200 to 300 megawatts of excess power is just wasted. So by incorporating batteries, data centers could serve an important role as an energy buffer, taking in low-cost power and potentially selling it back during peak demand. This approach would give data centers much greater control over the source of the energy they're using and make them part of the solution to renewable power instead of just adding to the problem. Another possibility is the use of fuel cells to embed electrical power generation and sharing at the rack or pod level, directly linking energy stored as fuel to computing. Besides the efficiency advantage, this approach eliminates any need for AC rectification or backup power. Other possible synergies include the waste heat that you generate during power production to drive cooling and water recovery. Although current pipeline fuels like natural gas are carbon-based, fuel cells can easily operate on wind or solar-derived synthetic fuels like hydrogen. So this approach would put data centers on a technological pathway toward 100% renewable energy that doesn't rely on the grid itself being renewable yet. The exploration of these technologies for use in data centers is currently being led by industry. As an example, this is a photo from Microsoft's facility in South Seattle, a 20-rack data center that is being powered by solid oxide fuel cells. This is a collaboration that involves Cummins as well as McKinstry, a design and build firm specializing in green infrastructure, as well as the state of Washington Department of Commerce. What I think this highlights is that to really make progress in this area, it requires a lot of cooperation and coordination across the entire cloud energy supply chain. So this includes cloud service companies, also providers of their infrastructure, developers of the technology that could be embedded in the data centers, and also the energy utilities. However, the pilot project I just mentioned also benefited a lot from interactions with Jack Brower at the UC Irvine Fuel Cell Research Center, as well as students at UCI and more recently UW. So while industry definitely can do this on its own, by including academia in the process also, we believe it stands to gain many benefits relative to just commercial exploration. And this is the central point that we're hoping to convey today and get some feedback from you about. In order to frame this discussion, imagine placing various R&D activities on a map spanning exploratory to commercial and also fundamental to applied. So we normally think of academia as sitting at the exploratory fundamental end, basic research, while industry is doing industrial development on the applied and commercial side. But recent decades have witnessed major expansions in the role of academia toward applied exploratory research, which drives pre-competitive innovation, while at the other end providing fundamental research tools to industry via shared use facilities. So common ways that universities bridge this gap to industry is through licensing, spin-offs, and other means of tech transfer, or by contract research, where academic researchers help industry solve particular problems they're having using shared research tools. So these are important modes of bridging this gap, but one limitation of this kind of interaction is that it's usually just narrowly defined innovations and commercial problems specific to one company or one university or startup company. But as I just mentioned, the problem of integrating energy technology into data centers is hugely multifaceted problem, and it requires a lot of cooperation by companies across the entire supply chain. In some cases, companies that have competing relationships. Also, for academia to participate effectively, it needs to bring a broad range of expertise and facilities that are not limited to any one faculty member or university. So addressing this gap really requires a different approach, and this is the essential motivation behind a consortium, where companies pool resources in a coordinated way to support a cooperative research center like the EIN. By bringing together a variety of different industries, companies, and academic institutions, we can address a much richer array of problems that really fill in the rest of this gap. Some of the things that this includes would be creating shared innovations that overcome technical or cost barriers and free the rest of the supply chain to grow, conducting realistic industry-informed techno-economic and LCA analyses that improve forecasting and allow the entire industry to make better strategic decisions, developing standards that distribute risk and allow various industries to move forward with development, tackling problems endemic to key products or processes so they don't limit development, and training people which have the right mix of skills and also practical industrial experience who can support commercial growth. These are all things that require cooperation and partnership among multiple companies and between industry and academia. Some of the things we hope companies will get out of our consortium include accelerated development and improved forecasting made possible by pre-competitive research and analysis conducted by the academic participants. Maximal leverage of shared state and federal research facilities toward the aims of consortium members, including garnering additional state and federal funding. Access to people with a broad range of skills with both information and energy technology, who in some cases may join the companies they've been working with. And an ongoing forum for exchanging thought leadership, developing standards, and forging new industrial and academic partnerships. The particular mechanism we're proposing for creating the EIN is the National Science Foundation's IUCRC program. This has proven to be a very successful model with 139 funded centers across the US, some of which you might know or are already members of. The basic idea is that government, industry, and academia work together in a partnership to fund and guide the center. The NSF catalyzes the center by providing seed and administrative funds, but the bulk of the funding for center activities comes from the industry members. Membership includes companies who have strategic interests in the center, but it can also include other entities such as trade associations or other state and federal agencies. Meanwhile, the university participants commit resources to the center in the form of research facilities and faculty and student effort. The faculty work with member companies to identify key areas for research, but ultimately it's up to the membership to decide what projects get the priority for funding. Although we've not finalized the format of the center, here are some of the basic mechanics. Members invest in the center through membership fees, typically $50,000 to $100,000 per year, depending on membership level. Members also commit at least one person to serve on the advisory board, which discusses and votes on the directions of the research for the center. The advisory board also identifies key topics for discussion at the annual meeting. Ideally, most of the research projects also involve active collaboration of the company members in the form of shared facilities and in-kind resources, active guidance by an industrial mentor, or students' residencies at the member facilities. Direct benefits to members include an annual meeting where faculty and students highlight research results and host in-depth discussions with their work and members, a cohort of PhD students with close ties to the member companies, early access to pre-competitive research results and analysis. In addition, companies also have non-exclusive royalty-free license to any IP that's produced by the center. To give you an update on our status, the EIN was awarded a small planning grant by the NSF, which provides support to gather membership commitments and host an in-person planning meeting where the NSF assesses the commitment level of the members to funding the center. A minimum of $450,000 in committed member fees are required to initiate the center. However, realistically, it's probably closer to $1 million needed to make widespread impact. This would fund a cohort of about 9 PhD students working in various areas of the center, which I think gets to the point where you have enough critical mass to make progress and also draw in outside funds from other entities. Unfortunately, we've had to put the planning meeting on hold due to current health concerns. Moving forward, our plan is to continue outreach and getting feedback from prospective members, and depending on the health situation, we'll either host a delayed meeting in early next year or forge ahead with signing members without a formal planning meeting. At the end of this webinar, we'll ask you for your feedback, including whether and to what extent your organization might be interested in supporting the center. In the meantime, though, I'd like to change gears, pass the mic to my colleagues, and let them describe in more detail the people and resources they bring to the center and why we think we're in the right combination of organizations to form the EIN. The next speaker is Jack Brower, a professor of mechanical and environmental engineering at UC Irvine. He's also the director of the National Fuel Cell Research Center in Irvine.
Thank you very much, Stu. And I'm happy to be here to talk about the contingent of experts from UC Irvine. You may not know that UC Irvine is perennially ranked one of the coolest schools in the nation by Sierra Magazine. And this is primarily because of its sustainability research and practices that we actually implement in the university. We also host the National Fuel Cell Research Center and Advanced Power and Energy Program, two important centers that contribute to this space of sustainable energy research, focusing upon fuel cells and hydrogen and batteries and renewable and zero emissions technologies. And the UCI faculty have expertise in lots of relevant fields, including electrochemical kinetics, in situ imaging, dynamic system simulation, thermodynamic system integration and controls that I'll briefly introduce in the next couple of slides. This experience that we have with running successful centers, I think, is an important part of what UCI brings to the EIN. We also have more than 7 years experience working in this space of introducing more renewable and sustainable energy conversion into data centers, in particular, working with Microsoft. And the co-PIs that we have in this UCI contingent have actually led things that have transformed other sectors, like, for example, stationary fuel cell markets in California and hydrogen fueling and infrastructure in California. In particular, Scott Samuelson has led in accomplishing this. We have world-recognized scientists that are developing electrocatalysts and catalyst supports, understanding the durability of these electrochemical systems, doing the characterization of these systems, and you'll see some beautiful images associated with what we can accomplish there. In situ X-ray imaging of fuel cells and batteries and electrolysis cells and flow batteries in operation. We have world-class, probably some of the best materials and microstructural characterization facilities and capabilities for discovery of electrocatalysts, applying them to real-world systems, and then even transferring that to actual applications with the companies that we have worked with over time. We also have, I think, kind of unusual for a university setting, the ability to develop and evaluate full-scale systems in this space so that we can actually take the discoveries all the way from the initial discovery of new materials to a full working system and evaluate how that works. Finally, we have lots of experience in simulating both the gas and the electric grids, and in particular, those gas and electric grids with high solar and wind renewable resources. So I'm going to introduce each of the faculty and then turn it over to Irina to introduce herself and give her a little bit of extra time as our featured faculty member. This is Brian Teroja. He primarily does dynamics and dispatch modeling of highly renewable electric grids, and you can see some of his results from the high grid model that he pioneered and continues to use. He also is expert in life cycle analysis of electrochemical energy storage technologies, and you can see that he's been applying these not only to fuel cells and electrolyzers, but batteries and flow batteries in his expertise. The next faculty that I want to introduce is Professor Scott Samuelson, who has pioneered a number of things that have led to the transformation of actual infrastructure in California and around the world. In particular, hydrogen fueling infrastructure, developing a strategic planning tool here, which we call STREET, and launching First Element Fuel as the owner and operator today of the majority of the hydrogen fueling stations in California. And you see an example of one down here. This is the UCI fueling station, still the most popular public fueling station in the entire United States. Also renewable hydrogen generation, in particular, leading an effort to develop this roadmap for production of renewable hydrogen over time. And also leading microgrid evolution. We have a fantastic microgrid here at UCI. It's been used to establish this generic microgrid controller with funding from the DOE. We've islanded our campus of more than 20 megawatts, and we have more than 4 megawatts of solar that we continually use. And we have batteries and fuel cells and other things to complement that solar on our campus. I'm the next faculty member I'm going to introduce, and most of what I have been doing historically is developing physical dynamic models of fuel cells, electrolyzers, batteries, and other energy conversion systems, and then using those dynamic models to complement high renewable use in various jurisdictions. And so you can see, for example, here, this is a 100% California grid that has to be complemented by various energy storage technologies like pumped hydro or hydrogen storage or battery electric vehicles that help the grid get through the year. I've also been pioneering some things in that integrate fuel cells, electrolyzers, and hydrogen storage with solar and wind, starting in the early 2000s with this experimental work that we did with funding from the US Department of Energy to look at hydrogen energy storage at the residential scale, for example. We've also been able to pioneer power to gas technology, and this is a picture of the system that we had operating on our campus. It was the US first pilot plant that we were able to demonstrate the production of renewable hydrogen followed by storage, injection into the natural gas system, and then coming back out in through a natural gas combined cycle plant, partially decarbonizing that plant with the renewable hydrogen fuel. And then finally, looking at data centers. You can see some of our original data center work that we did here with Microsoft. We were the first place in the world to actually power a data center server rack with direct DC power from a fuel cell. The next person I'll introduce is Professor Jabari Faryar. Has worked with us on a lot of different things for the dynamic models, but especially to apply control systems and control theory to actually make fuel cells, electrolyzers, and batteries perform better and to keep them thermally managed and things like that. He also has developed optimization techniques for things like district heating and cooling with unit commitment problems. And you can see also some battery electric vehicle charging algorithms for residential and commercial applications. And you see some of the fuel cell models, system models, okay, that you see here that have been developed, and the dynamics of these and how they may be applied under various circumstances represented here. The next is Professor Yoon Wong. Yoon is especially competent in computational fluid dynamics, but especially computational fluid dynamics applied to proton exchange membrane fuel cells, lithium-ion batteries, flow batteries, and hydrogen storage techniques. And so he has accomplished many different projects in which he has simulated using 3D modeling of two-phase flows and microchannels and porous media, and also accomplishing the heat transfer and thermal fluids simulation of these kinds of electrochemical energy conversion devices. And so you can see here several of his three-dimensional results, okay, that you can see, but also then the resulting performance characteristics that come from these kinds of simulations and experiments that he runs with fuel cells and other electrochemical devices. And now going towards a more fundamental level, Palmonov is a world-recognized electrochemist, and especially one who develops electrocatalysts and electrocatalyst supports. And not only that, he's also famous for transitioning those electrocatalyst and electrocatalyst supports into industry. And so you can see here structured platinum alloys that are actually currently being used by Toyota, he influenced. He also developed these platinum group metal-free materials that a company is exclusively using here, this pajarito powder. You also see the design for structure and reactivity that he and his group are famous for here. You also see some other companies that he is transitioning his expertise and discoveries to, like Bosch and Cabot, IRD, Nissan, etc. And with that, I'll turn it over to Irina.
Hello. Thank you for the opportunity to highlight the research expertise of my group. My group's expertise combines fundamentals and applied research to address technological challenges in the domains of fuel cells, electrolyzers, and batteries. In the PEM fuel cell domain, my group focuses mostly on the single cell testing, electrochemical characterization, and the use of synchrotron X-rays to probe morphological and chemical changes to electrocatalysts and carbon supports during fuel cell operation. So we also have significant investment into understanding degradation phenomena. For electrolyzers, we focus on understanding interface between the catalyst layer and porous transport layer. This interface is of critical interest because oxygen evolution reaction takes place in the anode catalyst layer, and because porous transport layer morphology dictates transport of oxygen and water. For batteries, we mostly partner with industrial companies to visualize morphological changes of positive and negative electrodes during battery cycling. So we developed X-ray imaging technique for imaging pouch cells. So you actually have real industrial size pouch cell, and we are able to collect and to establish correlations between the morphological changes of battery materials and electrochemical data. This slide highlights our collaborative work with Bosch to understand catalyst degradation during fuel cell operation by running so-called accelerated stress tests, or ASTs. We use Department of Energy protocol to cycle the cell with 30,000 cycles, 3 seconds each, between 0.6 and open circuit voltage. And this is the cycle representative of automotive degradation for catalysts during fuel cell lifetime. So we observe polarization decrease during accelerated stress test, and significant electrochemical surface area loss after 30,000 cycles. And this is the first study to use micro-synchrotron X-ray diffraction, and you can see the green and red pictures here of that, to map platinum size distribution of the membrane electrode assembly at the beginning of life. This is the left image, and also at the end of life. So what we see is the significant platinum agglomeration under the lens versus channel, and this is because of oswald ripening. So-called platinum dissolution occurs at locations under the lens, and they are cooler, and they have lower temperature, and this is why platinum migrates in ionomer and water phase under lens and redeposits to form larger particles. And we are excited that this continuation of this work has been funded by NSF intern program for my student, PhD student Prantik Saha. He's currently doing the internship at Bosch Sunnyvale, where he's studying the effects of carbon support and how it degrades during this accelerated stress test. Another major topic of my laboratory is understanding water management in PEM and also alkaline fuel cells. We published first study on using operando X-ray computer tomography technique to visualize water in operating fuel cells. These fuel cells featured PGM-free catalyst layers. So these catalyst layers did not have any platinum in it. And we observed significant water agglomeration at the interfaces. And this was due to these PGM-free materials and catalyst layers being significantly hydrophobic. So water size closely followed pore size distribution, and we suggested to improve the catalyst layer deposition methods to make sure that this 100 micron thick layers have as little interfacial gaps as possible, because water will pull in those interfacial gaps, blocking oxygen transport. Another recent study that we did in collaboration with the University of South Carolina was published in Nature Communications. Here we combine neutron imaging and X-ray imaging to probe water in alkaline fuel cells. Water management is challenging for alkaline fuel cells because water is produced on the anode side and is required as a reactant on the cathode side. So we observed significant anode flooding, and this was performance limiting step. So what we did, we changed electrode morphology and wettability by adding hydrophobic PTFE, and the performance improved threefold, and also water flooding was resolved.
Okay, thanks, Irina. Next, I'd like to introduce Greg Jackson, a professor of mechanical engineering at the Colorado School of Mines, and his colleagues to explain more about the resources on the CSM campus.
Thank you, Stu, and thanks for all who are in attendance. So we here at Mines, for those of you who aren't familiar, we are a technical school, largely full of engineers, so we don't try to compete with campuses like UCI for being the coolest campus. But we do have a tagline that's Earth, Energy, and Environment, and that tagline sort of captures a large sum of research and education that goes on at the graduate level at our school. In particular, we have a very strong collaboration with our neighbors here in Golden, Colorado, the National Renewable Energy Lab, and our collaborations with NREL really enable us to have a lot of diverse research opportunities that are related to the goals of EIN, and it includes a unique graduate degree program in advanced energy systems. So I've highlighted some of the faculty that have agreed to participate in EIN. You'll hear from Rob Braun and Amy Landis in a couple of minutes. I'd like to highlight that Mines has a strong presence in power grid and energy system optimization, particularly with respect to dealing with intermittent resources and energy storage, where the problem becomes very dynamic, and people like Salman Mohagegi is an expert in this field, particularly in dealing with uncertainties and applying it to systems that are very similar to data centers, power grid systems. Likewise, Alexandra Newman, who's the director of our Operations Research with Engineering program, is a key player in optimizing energy dispatch and storage models for systems that are trying to be lower in carbon footprint. One other person I'd like to highlight, two other people rather. Paulo Tabares is an expert in thermal energy storage management and integrating that with intermittent power sources in order to reduce both cooling loads as well as demands for energy storage electrically. And then lastly, Chuan Yu is an expert in cybersecurity and has a strong investment in looking at how cybersecurity integrates with energy technologies, particularly when you have distributed power and storage infrastructure. I'd like to talk a little bit not just about the research that's going on at Mines, but also the cross-disciplinary programs in terms of graduate education that we will bring to bear with respect to EIN, as we know that it's important for partner companies to not only see what research we do, but also what we do in education to provide training for our graduates. And so Mines has an advanced energy systems program that allows students to spend time at NREL and to work on technology development as well as fundamental science. And this includes efforts that we plan to bring in with respect to setting up a certificate in data center engineering. We also have a strong program in operations research with strong emphasis on OR applications in energy systems. We also have an energy engineering technology and management program that's relevant to many things with respect to data center operations and development. We have a data science program, and we also have a public policy program that really focuses on energy transition, the Payne Institute. We have a lot of courses that are relevant. I'll just highlight one. We have a very strong program in power systems design and operation in our electrical engineering department. It provides some useful training for students who are interested in going into data center engineering. I'll just highlight a few quick areas of research that are going on at Mines, and I tried to frame them in terms of questions that we think are relevant to the development of EIN as a consortium. And so one of the questions that you've heard from Jack and from Stu is, what is the role of electrochemical as well as thermal energy storage in making data centers more sustainable, more modular, and perhaps more reliable? So I talked about our work in optimization of local energy storage and dispatch of distributed power, and that's work that Salman Mohagegi and Alexandra Newman both work on. We also have work on phase change materials and thermal energy storage in order to mitigate maximum cooling loads, and this is important, particularly when you're talking about distributed power, in order to minimize the demand on those systems, and that's work that Paulo Tavares is doing. We have a very strong presence in fuel cells, as well as in reversible fuel cell or electrolyzers for chemical energy storage. And there's a whole team of us that work in that through our Colorado Center for Fuel Cell Research and Development. The other thing that I think is important for our center is the role of advanced modeling tools. And obviously, as academics, we're not going to be developing the sort of final stages of technology. We're going to be doing fundamental work, but we can develop modeling tools that can enable developers to explore the reliability and secure operation when they implement these alternative technologies. And I list a few. One I'll highlight here is we have very good world-class development of battery controls for safe and reliable operation with Tyrone Vincent and Bob Key. And one area that we're going to now highlight is our work in techno-economic analysis and life cycle assessment of energy systems. And Rob Braun is now going to present his work in that area that's relevant to the center. And then Amy Landis will follow with her work on life cycle assessment.
Thanks, Greg. Again, yeah, my name is Rob Braun. I'm in the Department of Mechanical Engineering. And in the brief time we have today, I'll just highlight some of the emerging tools and technologies that we feel are relevant for data centers. Two example research areas will be highlighted. These techno-economic tools that Greg mentioned in particular, we're working very closely with NREL at optimizing a so-called hybrid renewable energy and combined heat and power systems for distributed energy applications. This is a tool that will optimally size, procure, and dispatch various energy technologies to meet certain goals via the REOPT tool you may have heard about. Secondly, I want to focus on just a couple of exciting activities in electrochemical energy conversion technology R&D at Mines. This involves both hardware development at stack scale as well as systems. And this is for advanced power generation as well as hydrogen production for energy storage. So when we look at decision tools for techno-economic analysis, these are needed for the integration of high efficiency energy conversion, storage, and cooling for a host of applications, of course, data centers being one. And shown here, for example, is a data center energy system in the center. And you may have various center demands, which are typically met with utility requirements. But as we look to the future, increasing integration of wind and solar is desirable, and that necessarily necessitates some integration of battery technology. Or shown in the upper right, for longer duration storage, you may wish to take excess electricity and produce hydrogen. In addition, using low carbon fuels, perhaps as natural gas, but certainly landfill and biogas, can be used to drive and meet the base load power requirements, serving as a dispatchable resource, such as high temperature fuel cells, combustion engines and turbines, to meet those base load requirements. But thermal energy is a byproduct, and that thermal energy can be used for energy storage. It can be used for thermally activated technology, such as absorption cooling as well. And the main question is, how do you decide? How do you pick size and dispatch such technologies to meet whatever your goals are, whether that's minimum cost, maximum resilience, or maximizing sustainability? And so MINDS, in collaboration with NREL, is significantly updating the REOP tool to enable evaluation of these array of technologies for all kinds of end-use applications. And shown here is this kind of flow chart where you have in black the REOP Lite tool that does the techno-economic optimization, but on the left-hand side are the technology options. And we've been building out the array of technologies shown on the left, including part load characteristics, off-design characteristics of all the base load prime movers, such as fuel cells and turbines and so forth, that would be sensitive to ambient temperature changes, operation at elevation, and heat recovery as well, both at design and part load. And then the drivers are shown on the top, and you can pick various goals to minimize cost, maximize resilience, and so forth. And on the right-hand side are looking at the optimized minimum cost solutions, which involve a certain technology mix, sizes, and then dispatch operations, which are typically formulated through some mixed integer program that needs to be solved. This optimal design and dispatch can be applied to all kinds of building applications, including data centers shown on the right, or other applications such as hotels and hospitals and so forth. So on the right-hand side, you have these building power loads, heating demands, cooling demands, and on the left-hand side, utilities. And in the middle is this array of technologies which are being expected to serve those loads. And the tool basically picks the sizes and dispatches and procures this technology through annual simulations. The hybrid system then, just for an example shown here, is a renewable energy system that is combined with cooling, heating, and power through engines, PV technology, battery energy storage, and absorption chilling for a hospital in Northern California. And the black lines shown in the bottom left-hand curve show the electric power demand on order of a megawatt. The right hand is the cooling demand in terms of tonnage. And you can see you're over a megawatt in electric power, and on the right-hand side, your cooling is over 150 tons. The tool essentially optimally procures and selects the array of distributed energy resource technologies and then dispatches them to maximize the life cycle savings. And here you can see for this particular situation, using utility rates and weather files for this location, it picked so much of internal combustion engines and PV and battery and chilling, and achieves life cycle savings on the order of $6 million. This is the kind of capability and framework we're currently working to establish. It certainly can be applied to other applications like data centers. Switching gears now and looking at just a brief highlight on some of the exciting work in Protonic Ceramics, which are really next generation electrochemical technologies we've been working on in collaboration with industry, and has numerous applications including power production, electrolysis for hydrogen production, as well as electrochemical compression technology on both the hardware and systems level. And these Protonic Ceramics, they operate at lower temperature. They are proton conductors, so they act like a high temperature PEM fuel cell. And we work at developing and scaling up the technology, and we're currently working with Fuel Cell Energy to scale to commercial scale stacks, as well as the systems that include process engineering, as well as the techno-economics, which allow us to build out the systems and help accelerate the deployment by optimizing the design of the system for minimum capital or maximum efficiency or whatever the objective might be. Just as an example, the scale-up activities in this space have shown that in the past few years, we have not seen the decrease in power density, and we're ready to move towards building stacks and systems, which is currently underway at mines. Our current state is we're building 1 kilowatt Protonic Ceramics stacks, and they have a lot of promising results in a number of key areas, including low-cost stack technology, cheaper than solid oxide cells, we believe, exceptional fuel flexibility. They've been run on alcohols and liquid fuels directly, and they operate at potentially high efficiency without hybridizing the system and low cost. And the next step is to push them towards multi-kilowatt systems that could be compatible with rack level power requirements. Additional activities we're focused on at mines involve electrolytic hydrogen production, so we can run these Protonic ceramics in reverse, and they can serve not only as our internal reforming device, but they separate and do a light electrochemical compression step before passing it on to other technologies, either reciprocating compressor technology or PEM compressors, which could serve higher pressure hydrogen requirements. We're also running them as pure electrolyzers and scaling that activity up to stacks, as well as testing them in the facilities on hand at mines, and doing life cycle costing analysis of hydrogen production for these kinds of systems. Lastly, in addition to this activity, we're certainly heavily engaged with industry at building out full-scale systems of solid oxide fuel cell hybrid systems designed to take different kinds of fuels, such as natural gas, and generate high efficiency and low-cost power at efficiencies greater than 70% and capital costs less than $900 per kilowatt. We're in the middle now of the next phase, and we will be demonstrating at full scale this technology in collaboration with our partners. That's it for my highlight. I think the next is Amy, who's going to talk about LCA.
All right, I'm not muted anymore. I'm Amy Landis. I'm a professor at Mines. I'm going to speak about life cycle assessment and the work that we do and can support the teams on this project in terms of ensuring that projects that go forward are environmentally friendly. So life cycle assessment quantifies the environmental impacts of a product, process, or system. And we can actually apply LCA at early technology readiness levels to give advice and guidance on hotspots. And often these hotspots that we identify are associated with cost savings. They're usually energy consumption, oftentimes, emissions that impact air quality and health of workers. So I'm going to skip over this to the sort of how the nuts and bolts to maybe try to get us back on time. But I wanted to highlight why people do LCA. So as I mentioned, we can do what's called screening LCAs to give folks an idea of early technologies and where they might be able to be re-engineered or redesigned to minimize environmental impact. But people often do LCAs on a comparative basis. Is one alternative design better than another? Or you might want to compare to a competitor's product. Is my product more environmentally or less environmentally friendly than a competitor? As I mentioned, at the full scale, we also do LCAs to understand areas where we can make improvements to the environmental footprint of a product or process. And then we also use LCAs for documentation. So outside of the US, a lot of different countries have guidelines and guidance on industries to specific facilities and how much emissions and sometimes you're even often required to do a life cycle assessment for new products in other countries. And so life cycle assessment is the tool that informs those types of policy guidelines, emissions reporting. One of the formal reports is called an environmental product declaration. That's here. It's governed by the International Organization for Standardization. It's the 14040 series. And then there's also this newer group focused on carbon and climate change, the ScienceBased Targets initiative. I encourage you to go look at the website. There are a lot of companies within the data center space that are already making commitments and doing this type of work. And so in order to publish a science-based target, you have to do these life cycle assessments. So this is just some preliminary work. It's the pie chart here to show carbon footprint of a data center. this is not my work, it's similar to work that we do, but you can sort of see how at least from a carbon footprint standpoint, life cycle assessment can tell us where the hotspots are here. The other topic I was asked to speak on was diversity, inclusion, and access. So at Mines, I'm the Presidential Fellow for Diversity, Inclusion, and Access. I lead our campus efforts. And it's something I can offer to this team as well. Hopefully you all are aware of the benefits of integrating diversity inclusion into research and into new technology development. It's not just the right thing to do, but adding diversity and inclusion develops for students richer learning experiences. Research shows that teams are better at problem solving, and that the problems that they're faced with, these diverse teams tend to generate more innovative solutions to complex problems compared to teams that aren't very diverse. And research actually shows that diversity in companies and organizations, those groups have better in financial performance. When you achieve diversity, it doesn't necessarily mean that you're going to sustain diversity. Inclusion is how you retain them and keep them involved in these projects and keep them working at your company. And finally, the two sort of topics on the right here, we recognize that diversity doesn't just happen. You have to monitor it. You have to report on how well our research teams and our consortium are doing with respect to achieving diverse and inclusive research cultures. And then we want to reward and recognize those efforts so that everyone in the team and everyone outside of the consortium knows the successes that we're having.
Hey, thanks, Amy. The next speaker is Dan Schwartz, the Boeing Sunder Professor of Chemical Engineering at the University of Washington and Director of the Clean Energy Institute. He will describe some of the resources that the University of Washington brings to the EIN.
Thanks so much, Stu. Really appreciate hearing from all my colleagues. Clean energy is really one of the imperatives of our state, as articulated by our governor. It is the right thing to do for our children and the future health of the planet. So the state has made major commitments to clean energy innovation in the state of Washington. We have had a $31 million sort of capital investment to create the kinds of infrastructure that can be leveraged by both industry and university researchers. It's open access with very flexible intellectual property terms and non-disclosure versus publicly accessible data. So we call them the test beds because there are three forms of test bed in there. We have the research training test bed, which really provides an extraordinary, what we call molecules to miles understanding of energy, so that an electrical engineer that understands techno-economics of grids and energy systems can build and understand what's inside of a battery, and vice versa. A materials chemist can understand the fundamentals of what goes into durability and the techno-economics of how their devices, materials, and systems can scale. So we make great people through that. We also have a scale up and characterization test bed that can take from the lab scale to the device demo scale up to manufacturing scale. So we've partnered with startups in the Bay Area where we are their test manufacturing site, for instance, for product development at scale. The systems integration test bed, which is a critical resource for things like the EIN, has the ability to do real-time digital simulation and integrate power hardware with simulation so that you can swap in and take out components, whether it's a server rack that is powered by an emulated power system, where we can do up to currently about 40 kVA, 40 kilowatts of power, as well as having a battery energy storage system. These are facilities that can be accessed by anyone in the community, all with online availability. The thing that makes this work both for our industry partners and for the university researchers is an expert staff. We recruited serial entrepreneur Devin McKenzie to come up here and help build out a team that could support people, and this team is amazing. They are part really of our critical channel partnerships with tool makers, with industry partnerships, and they're part of going faster at the Clean Energy Institute. Somebody not shown up here, for instance, was recently hired away by Amazon. We hate to see them go, but they're part of accelerating a clean energy future. So when you put this together, you get company responses like these. PO Celtech is a spin-out fuel cell company in Israel. They came to Seattle because of a channel partnership that we had with a tool vendor that wanted to demonstrate their tool at the best run facility in the world. PO Celtech came and they said they accomplished as much in 3 days as it would have a year at home. They now, as trained users, can sign on to use our facilities through software and come to Seattle to implement. We have small companies like Vesicus that use this to leverage STTR and SBIRs, and then sort of global distributed companies that have engineering support teams in Seattle because the test beds let them work effectively. We have about 390 individual users in the facility, comprised of academic science and engineering users from around the country. 50 companies. I can't give you most of the names because they're under non-disclosure agreements, but I think we have currently 4 of the 5 Fortune 5 companies in this place. Microsoft is the one that is so open, and we're appreciative of the ways we partner. Part of this is creating a vibrant ecosystem. We like to think at the Clean Energy Institute, we are the low emissions technology-based economic development agency of the state of Washington. And that means everything we do brings external people in and sends our students, trainees, and others out, and we interact very strongly with a variety of organizations and networks like Prime Coalition in Boston, Cyclotron Road, others around the nation. We have access to experts like Scott Case, who was the founder and COO of Energy Savvy before they were acquired. He's now building his next team and providing advice to our students, trainees, and everything we do also invites external partners into the university. So he's available for startups outside of UW as well. Jeff Kanan is a board member at E8, an investment group in the region. Jeff and I actually participated in the inaugural group of the I-Corps program at NSF. We went down to Stanford together with a student trainee. He provides guidance on a regular basis for startups. We also have grad education programs like our NSF NRT, Direct Data Intensive Research Enabling Clean Technologies, and our civil engineering department has created an online energy infrastructure degree. We're very flexible as an institution to create tailored professional education. The energy infrastructure is an online master's, and we partner with our business school and organizations to get our students out into the business community with things like the Torrance Foundation Technology Due Diligence Program, where our students provide diligence. They hear the investor conversations from the behind the scenes to understand how they can go faster with their innovations. And finally, the proof is in the pudding, and we're really proud of the national recognition our early career people are having through things like the Forbes Energy 30 Under 30. These are early career people that are really making a difference to the nation, and CEI is here to support the EIN in all of its efforts to build this kind of a collaborative community.
Okay, thanks, Dan. So Dan just described some of the institutional resources UW brings to the EIN, but what I'd like to do now is also highlight a few of the faculty who have scholarship in areas overlapping the EIN and thus are likely participants. One area of strength for UW is in electrical engineering, where we have a number of faculty interested in issues related to sustainable energy and grid storage. Baosun Zhang and Daniel Kirschen both study the problem of integrating renewable power into the grid and the role data centers might play in that. Daniel looks at this problem from the grid perspective, how flexible loads and storage might be used to balance production from intermittent sources like wind and solar. Baosun's work, some of which has been funded by Microsoft, is more focused on the local problem of peak shaving and how data center storage might take advantage of the excess power market and the N+1 redundancy of distributed storage. Brian Johnson, also in electrical engineering, looks at this same problem from an even more local perspective, in particular how modules in a DC power network are best coordinated. A general problem with DC power networks is power sharing, how multiple sources in a distributed network share loads, or conversely, how sources can be shared among multiple loads. In DC power networks, a common approach to this problem is to use centrally controlled interleaving of current, but this can become complex when loads and sources are constantly fluctuating and are also being added to or removed from the network all the time. The control systems also become a single point of failure. Brian's been developing modular DC power control systems that are based on self-organizing modules that detect and auto-sync with the power network, requiring no central control mechanism. Enabling technologies like this are going to be very important if we're going to commercialize distributed storage or generation into a data center. Likewise, Devin McKenzie, a professor in mechanical and materials engineering, is focused on enabling technologies for electrochemical materials. One of the major barriers to widespread adoption of batteries and fuel cells into a data center would be manufacturing cost. Devin works on new scalable approaches to production of materials with optimized 3D microstructures, methods that can be used both for rapid prototyping and then be expanded into mass production. Working closely with industry, much of his work is focused on battery and photovoltaic materials, but many of the same issues apply to materials for flow batteries and fuel cells. We've seen this many times in history where a major breakthrough in manufacturing has a really big impact on the cost to performance ratio and suddenly brings new technologies within the range of widespread deployment. The Department of Chemical Engineering, there are several faculty, including myself, who are interested in enabling electrochemical technologies, including batteries and fuel cells. You just heard from my colleague Dan Schwartz, who's a long history in this area. One theme that unites our work is the use of experimental diagnostics and modeling to get at underlying causes of failure in batteries and fuel cells, which is a major source of concern for their use in data centers. As an example, one of my students has recently been using on-stream impedance methods to identify particular types of failure in operating fuel cells that can be performed without interrupting their operation. We found that by using machine learning, impedance response can then be tied to specific modes of failure, potentially allowing a fuel cell module to be swapped out and fixed before a catastrophic failure occurs. So very much in line with the way a data center operates, where reliability is achieved through massive redundancy. Another area we're examining is the balance of plant design, including possible synergies of embedded power production into data centers. Dan just started an ARPA-E program with folks at Pacific Northwest National Lab looking at optimized design of solid oxide fuel cell systems. Besides being more efficient, solid oxide fuel cells produce a lot of high quality waste heat that can be used to drive water recovery and cooling. This has a huge potential benefit for hot and humid climates where air refrigeration is often needed to cool server racks, compounding energy use and carbon footprint. One of my students has recently been modeling this and shown that depending on how intimately water recovery and thermal management are coupled, it may actually be possible to eliminate nearly all of the water use and defray a majority of the cooling load. And this is without any moving parts as in a normal refrigeration cycle, just water feed lines and braid lines to and from the racks. In the interest of time, I'm going to cut it off here. Hopefully you found this brief tour of research at our 3 campuses interesting and informative. What I'd like to do now is turn things over to Todd Cleland for a Q&A session.
Yeah, this is Todd. Thanks, Stu. This is Todd from the UW. Just wrapping up our webinar today with some audience participation and Q&A. You should be seeing a live quick poll with a multiple choice question. I can see the answers are coming in now. So it looks like the majority are coming in, 42% for providing new energy technology, 27% for data center infrastructure, and in third place we have other. So the top 2 are new energy technology and the data center infrastructure. And then one more audience participation question here, asking you all out in the audience about what motivation you might see for a consortium like the one that we're proposing today. So we've got about just over 60% of the audience has voted, up to about 2/3 now. It looks like the top item in the voting right now, up to 74%, is the annual forum for concentrated interactions with companies. So that's popular, closely followed by the access to experts, about 52%, and then third third most popular is the pre-competitive research, or access to pre-competitive research. So that's about 90% of the folks have voted so far. So we have a few minutes left here at the end for a Q&A. So if you'd like to ask questions of any of our expert panelists, you can enter those into the chat. Here's one that first one that came in, and the question here is why a consortium approach? Couldn't the same work be funded by more traditional mechanisms such as contract research with an NDA and licensing of university intellectual property? Who wants to take that one?
Hey Todd, can you return to the camera view, or
oh,
sure.
Can do that?
There we go. Awesome.
Thank you for the reminder. I will close the poll.
That sounds like one for Stu. Why the consortium approach?
Why the consortium approach? So I think the basic idea is that by focusing on shared research, the consortium can have a much wider impact than it would if it was just working with one company. Companies pool resources and benefit jointly from the orthogonal activities of the center rather than separately investing in the same area. The other thing is that we're doing here is we're maximally leveraging funds by industry. So unlike a traditional contract R&D, overhead is capped at 10% by the National Science Foundation. There's also a huge opportunity to draw in additional state and federal funds. So for example, it's pretty likely, I think, if we got this center funded at sort of the $1 million level, the state of Washington Clean Energy Fund would match the company contributions up to 1-to-1 for durable infrastructure. So all of a sudden, the $1 million center becomes $2 million. So there's this sort of leveraging effect that I think is key to creating an inertial mass that you just don't have if you're doing things on an individual basis. And the other thing is a huge list of indirect benefits. I think you just heard from that poll. A lot of people, I think, are interested in this because of the forum, that we would have every year where companies come together and discuss this and set standards and really sort out how this is, road mapping how this is going to go in the future. So these indirect benefits of access to people, access to experts, new business connections, forecasting, it's a very small contribution, relatively speaking, with a huge potential upside.
Stu, if I could comment, even though my camera's not working, I would just say that it's an and operation. Everything Stu said, and you can make individual side things as the research progresses. You can then add the and function and say, we want to customize it to our particular need.
Okay, here's a question that just came in. What is the level of interaction with utilities as stewards of the grid to deploy said technologies across service territories?
So maybe I can comment a little bit on that, because we have a very strong interaction with Southern California Edison, also many projects with Pacific Gas and Electric here in California, and also with Southern California Gas Company. And so we've had a lot of advanced technology investment from them, but also collaborative research with them in which we deploy some new technologies within those existing utility infrastructure. So we have a very close working relationship with those both gas and electric utilities in California. And I know you have some similar ones in Colorado.
Yeah, if I can add to what Jack just said, I think if you look at the state of the utilities in Colorado, our dominant utility, which is Xcel Energy, has made commitments to increasing renewable energy penetration. And one of the big questions is how to implement that with the advances in energy storage, which aren't really yet spelled out. And so the role that data centers and other high energy demand systems might play in being sort of both, as Stu spoke about earlier, storage as well as demand side management potential, is something that I think utilities are really looking for solutions and looking for long-term research to sort of address these kind of questions.
And I think also the solutions themselves, it needs the input of all the stakeholders. So I think that's one of the aspirations of the center too, is to get both the end users, the utilities, and the OEMs involved.
think we've got maybe time for one more quick question. This one has to do with what it says. It seems like in many cases, research results or IP generated by the consortium, the EIN, will only directly benefit certain companies or sectors, for example, battery or fuel cell companies. Why should other companies in the supply chain be asked to pay for this? Why not just wait until technology developers make progress on their own and then jump on it when it's ready?
Sure. Yeah. I think the basic answer is that because you're accelerating the progress of companies that still, they're your suppliers. So it indirectly benefits other companies in the same supply chain by enabling these new technologies and products that save them money and enable them to do things that they wouldn't otherwise be able to do. In fact, you could argue that by helping all the developers in the same area, you're ensuring a broader based market for the same technology that drives costs down and further accelerates the development. So it's sort of a snowball effect.
Great. Well, I think we're just about out of time. I've got just a couple of things to wrap up here today. Just to call your attention to a couple of upcoming UIDP events and webinars. There's one coming up on August 26th with NIST to introduce the NIST Extended Reality Community of Interest. That's at 12 Eastern. In September, we have the UIDP Fall Conference, which is virtual, UIDP Connect. That's the week of September 21st. There'll be various sessions and panels going on all week that week, some number of great keynotes and over 50 speakers. So I'd certainly encourage you to check that out. Finally, as Stu mentioned, there will be a post-webinar survey. We'd really appreciate your feedback on the webinar and certainly to hear from any of you that would like to learn more about the consortium. And we'd be happy to follow up and talk further about our plans and how we will work with the industry. Thanks, everyone.
Thanks, everyone, for attending. And
thank you.
appreciate your feedback. Thank you.